Today our lesson is on Lewis structures. First we'll be looking at ionic versus covalent bonds, and then ionic versus covalent compounds, and then we'll learn how to draw the Lewis structures. They're also called electron dot diagrams. Okay, so an ionic bond, as we learned, involves the transfer of electrons. The transfer of electrons from a metal to a non-metal. All right, a covalent bond, on the other side, involves the sharing of electrons. Sharing of electrons. And that is usually between two non-metals. Usually between two non-metals. So remember, we're going to use the staircase. To the left is a metal, except for hydrogen, and then to right is a non-metal, including hydrogen. Okay, so for our ionic bond, we need a metal and a non-metal. So that means our elements are from opposite sides of the periodic table. So opposite sides of the PT, periodic table. Whereas for a covalent bond, our elements are going to be on the same side. Same side of the periodic table. And hydrogen. Except hydrogen, right? Because hydrogen is a non-metal, so hydrogen is on opposite sides of the periodic table, but hydrogen is involved in covalent bonds. All right, so for our ionic compound, our ionic compounds are composed of ions, because we have all this transfer of electrons from the metal to the non-metal. The metal loses electrons and becomes a cation. So we have cations that are positive, and in our compound we have anions that are negative. And all the cations and all the anions will all add up to give a net charge of 0. In our ionic compound, the smallest particle that represents the compound, also called a representative particle, the smallest particle is called a formula unit. It's called a formula unit. And that is the lowest whole number ratio of the ions. And so, for example, we have MgBr2. So we have one magnesium ion and two bromine or bromide ions. Another example, Ca3N2, and good old table salt, NaCl. So all of those represent one formula unit of an ionic compound. All right, so our covalent compounds. Our covalent compounds are composed of molecules. So what is a molecule? A molecule is a group of covalently bonded atoms. So a molecule is a group of covalently covalently bonded atoms. So the smallest particle of a covalent compound is a molecule. The smallest particle of an ionic compound is a formula unit. So we'll give some examples here. So water, good old water, H2O, and N2O4. So we do not have to have lowest whole number ratio for molecules, but we do always have lowest whole number ratio for ionic compounds. All right, so now let's learn how to draw Lewis structures, also known as electron dot diagrams. Okay, so we're going to start out with the simplest molecule that there is, and that is a molecule of hydrogen, which has the formula H2. We have 2 atoms of hydrogen. So if we look at our electron dot structures, hydrogen has 1 valence electron, so we get 1 dot. And if we have 2 hydrogens, they're represented are 2 atoms of hydrogen, each with their 1 valence electron. So for a molecule of H2, these 2 hydrogens are going to share their 1 valence electron because hydrogen wants to be like helium. Helium is 2 valence electron and helium is very stable. So they're just going to share their electrons. So this hydrogen with its 1 electron is going to share with this hydrogen with its 1 electron. And this represents our molecule of hydrogen. This is the Lewis structure for H2. We can also write this as H dash H. The dash is the same thing as writing these 2 electrons in between the 2 atoms that are sharing their electrons. Either way, this is called a single bond. So for a single bond, we have 2 shared electrons. And for hydrogen, when it has 2 electrons, its outermost energy level is full. The first level can only hold 2. So I guess we could say that each hydrogen has a duet. Not the octet. Each hydrogen has a duet when it bonds. All right, now we're going to take a look at another example. So now we're going to look at a molecule of fluorine. Fluorine is F2. So we look at fluorine's electron dot structure. Fluorine is in group 17, so we put in 7 valence electrons for 1 fluorine. And then we're going to do the same thing with our other fluorine, because we have 2 atoms of fluorine in 1 molecule. So fluorine would like to have the octet. It has 7. It would like to get 1. This fluorine would also like to get 1 electron. So the fluorine's going to share 1 electron apiece. When they do that, our structure looks like this. So 1, 2, 3, 4, 5, 6, 7. And now this fluorine has 1, 2, 3, 4, 5, 6, 7. So here is our Lewis structure. And we could also write it showing the bond between the 2 fluorines as a dash, but we have to keep these other electrons that are not in the bonds as dots. So either of those 2 is a Lewis structure for the F2 molecule. And again, we can see that we have a single bond in between our fluorine atoms. Now, these other electrons are very important electrons, and we look at these in pairs. So we call these electrons lone pair electrons. We can also call them non-bonding electrons. And another way that we can refer to them is unshared pair. electrons. So these all mean the same thing. So fluorine, this fluorine has 3 lone pair electrons, and this fluorine has 3 lone pairs of electrons. Okay. All right, now let's look at a molecule of water. So we know that water's formula is H2O. And this time we're going to use a little different method for doing our Lewis structure. We're going to do a valence electron count. And that's how we'll be doing most of our Lewis structures. So this is how we're going to do that. So hydrogen has 1 valence electron, and we have 2 hydrogens for a total of 2 valence electrons. Then we have oxygen. Oxygen has 6 valence electrons, and we only have 1 oxygen in our molecule for a total of 6 valence electrons. So we have a total of 8 valence electrons. Now, these are the electrons that are going to be bonding or lone pairs in our molecule, and we don't have any more or any less that we have to put in our Lewis structure. So we have an H, an O, and an H. The oxygen goes in the middle. And now we want to put in our 8 valence electrons, and we have to have a bond between the oxygens and the hydrogen. So 1, 2, 3, 4. And now I still have 4 more. Hydrogen's finished though. Hydrogen is only going to have 2 electrons between it and another atom. So we have to put in our other electrons. And that is the Lewis structure for water. We could also write it as H-O-H and put in our lone pairs of electrons. Both of these are valid Lewis structures. And we can see the oxygen has 2 bonding sets around it and 2 lone pairs of electrons around it. All right, and it wouldn't matter if we did it like this. These represent the same thing. They both represent single bonds between the hydrogen and the oxygen, and an oxygen that has 2 lone pairs of electrons on it. Okay, so let's now do our next molecule, which is NCl3. All right, so we're going to do our valence electron count. So nitrogen, I think we'll do it this way. We have 1 of those, and chlorine, we have 3 of those. So if we look on our periodic table for our valence electrons, nitrogen in group 15 has 5 valence electrons. So 1 times 5, we have a total of 5 valence electrons from the nitrogen. Chlorine is in group 17, so we have 7 valence electrons. So 7 times 3 is 21 valence electrons. So we add them up, and we get 26 valence electrons that we need to have in our Lewis structure. No more, no less. All right, so we're going to put the nitrogen there in the middle, and then we'll put our chlorines around it. And now we're going to put in our 26 valence electrons, and we want to give each of these atoms the octet. All right, so we put them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And if we look at each of our atoms in this molecule with sharing electrons, they all have the octet around them. So this nitrogen has its lone pair of electrons, and then it's got its shared electrons. So if we look only at this nitrogen, it has 2, 4, 6, 8. It has the octet. If we look at this chlorine, it has its own lone pairs of electrons plus the electrons that it's sharing. So this chlorine has the octet, as does this chlorine and this chlorine. So we always want to make sure that our atoms have the octet around them, counting their lone pair electrons and the electrons in the shared pair, the bonding pair. And remember, except for hydrogen, hydrogen's only going to have 2 electrons. All right, so we could also write this as N dash, Cl, 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 and then put in those lone pairs of electrons. Okay, so both of these are valid Lewis structures. Okay, so now let's take a look at a molecule of oxygen, O2. So we have oxygen, there's 2 of them in our molecule, times each oxygen has 6 valence electrons. Oxygen is in group 16 for a total of 12 valence electrons. Okay, so we put our oxygen atoms in, and now we're going to go ahead and put in our 12 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we check each oxygen to see if each oxygen has the octet. So our first oxygen here has 1, 2, 3, 4, 5, 6 valence electrons. Yeah, the sad face. He wants 8, but he only has 6. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is fine. This oxygen has the octet. So we only have 12 valence electrons. We can't just add 2 electrons over there. We don't have them. We only have 12. So what we're going to do is we're going to take 2 electrons from our oxygen that's happy, and we're going to move them into the middle so that they can be shared. When we do that, and we have 4 in the middle, this oxygen still has its 4 electrons, and now this oxygen still has 4 electrons. So now when we look at our first oxygen and we look at all the electrons, 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen has the octet, it's good, and this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So it is good. So these shared electrons we count for each atom when we're counting up the electrons that they have around them. So we can write this as O, 2 lines, O, and these 2 lines represent 4 shared electrons, and this is what we call a double bond. We have 4 shared electrons, or we could say we have 2 shared pairs of electrons for our double bond for oxygen. All right, now let's do a molecule of nitrogen, N2. So we're going to count up our valence electrons. So nitrogen, we have 2 of them. Nitrogen in group 15 has 5 valence electrons. 2 times 5 is 10 valence electrons. Put in our nitrogens, put in our 10 electrons, and initially just kind of divide them up evenly. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and when we do that, we can see that this nitrogen 2, 4, 6 is not good, does not have the octet, and this nitrogen 2, 4, 6 is not good, it does not have the octet. So whenever that happens, when you run out of electrons, that's when you start moving electrons into the center so they can be shared by both atoms. So we can move these 2 into the middle, and that would leave us like that. So this nitrogen would have 2, 4, 6. That's still not good. This nitrogen, however, has 2, 4, 6, 8. This nitrogen is good. So we still have more work to do. We need to get this nitrogen to have more electrons. So what are we going to do? We're going to take some electrons and we're going to move them into the center again. So when we do that, now we're going to have 3 pairs of electrons in the center and with our lone pairs of electrons. And it doesn't matter where we draw those. So now we have a triple bond between the nitrogens. So we have a triple bond. So we have 3 shared pairs of electrons. And each nitrogen has the octet, 2, 4, 6, 8, 2, 4, 6, 8. So everyone is good there. Okay, so we'll do one more example. This one's a little tricky. We're going to do SO2, sulfur dioxide. So we're going to do our valence electron count. So sulfur, we have 1 of those. Oxygen, we have 2 of those. Sulfur in group 16 has 6 valence electrons for a total of 6 valence electrons. Oxygen is also in group 16, so we have 6 valence electrons. 6 times 2 for a total of 12 valence electrons for a total of 18 valence electrons. All right, so we're going to put sulfur in the middle and each oxygen on the side. And then initially I'm just going to put them in kind of evenly. So let's see how we do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so we look here and we can see that this oxygen is 2, 4, 6, 8. It's good. Sulfur is 2, 4, 6, 8. It's good. Oxygen is 2, 4, 6. No good. So what we need to do now is move some electrons into the middle to give this oxygen more electrons that it can count. So let's take these 2 and move them in. When we do that, that brings 4 into the middle. Oxygen still keeps the electrons that it had. Sulfur still keeps the electrons. Everything else stays the same. So there we go, 2, 4, 6, 8, 10, 12, 14, 16, 18. This oxygen has the octet 8, sulfur 2, 4, 6, 8, the octet, and oxygen 2, 4, 6, 8, it has the octet. So this would be O, single bonded to S, double bonded to O. And remember, we got to put in those lone pairs of electrons. They have to stay. So there is our Lewis structure. We have 1 single bond and 1 double bond. Okay, so when you're doing Lewis structures, this is your process. You want to get your valence electron count, then write your atoms, and then put in your valence electrons. And if you do not have an octet, or for hydrogen a duet, then you have to start moving electrons into the middle and making double or triple bonds. All right, that's it.